Okay, so the first of our overview talks is going to be given by Ron Stouffer on what's going on with AOGCMs.
Okay, I want to thank you for inviting me here today. And I was talking to Peter last night, and I said this is a deadly talk because it's mainly words and not many pictures. And so I decided to show some pictures from the last 2 days. So it looks better on the screen than there, but that's looking west from Pikes Peak.
Seeing aerosols?
Well, like I said, it's a lot better on that screen than there. So the outline of my talk is I'm going to first hit the what I call the modeler's dilemma on how to spend resources, and then talk about the new physical climate components that I see, and I've heard talk to a number of people in our community about what's coming in for AR5. I'll just touch on the philosophy of how to construct an ESM, and I think other people will be doing that also. And there's the issue of what is an ESM, of course. Talk about initialization of the physical climate models, and I think there's lessons to be learned for initialization and how to do the Earth system models, kind of things you want to hit on. And the types of integrations we performed in common, what kinds of things we learned from those in the AR4, and then various data issues at the end. So this is what I call the modeler's dilemma, is how to spend additional, it could be just resources. People focus on CPU resources. It could also be data storage resources. There's kind of three main ways, if you give modeler more CPU time, how they could spend it. They could spend it on higher resolution, and doubling of the horizontal resolution usually gets you something like 4 to 8 times higher cost. It depends on how the time stepping in the model is going.
Well,
yes?
Why don't you include vertical resolution in the domain?
I will. This is just an example. I'll get there in a bit. The number of ensemble members, and of course that would just scale linearly with the number that you have, and more components. At GFDL, what we've been calling our Earth system model cost about a little less than 3 times more than the physical climate model alone.
That includes the chemistry?
No, there's no chemistry in that. That's just a carbon cycle. And dynamic vegetation, and I don't know what other parts you want to throw.
Does include the dynamic vegetation?
Yes. My perception from talking with modelers are that by far and away when you go out to get money, people the funders tend to like to hear about higher resolution. There is some evidence, I think recently when I listened to what's going on around the planet, that more components can also get you more money, but I think it's something like 4 times to 1 time here. It's a pretty big ratio.
Well, in the UK, the ensemble can attract the funding as well.
It can. I don't think that's typical, but you're right. I have talked to the folks. Of course, adding in new components is the component builder's favorite. The folks that build the chemistry models, the carbon cycle models, the aerosol components, whatever. And then the constituency that likes the more ensemble members are typically folks that involve detection attribution because they like to more cleanly define the signal and the noise in the system. And of course, if you have more ensemble members, you can start making probabilistic statements about climate changes. So for the physical components, I'm going to focus on just the atmosphere, the ocean, the land, and the sea ice. The land ice is something that's not in, I think, any of the AR4 models, but it's something that's coming. It's unclear to me if it's going to make it by AR5 in many models, and there's a real issue whether it's important on DEXN, the typical IPCC timescales, clearly on longer timescales as it is, beyond 2100. And I said, people argue about whether it's going to be important or not between now and the 2100. The main thing that I see as a problem coming that is not addressed in our community very well at this point is grids for the new models. In the AR4, the ocean components on a lot of the models aren't latitude-longitude grids, and this caused a problem. The reason for going to non-latitude-longitude grids is that they can be computationally more efficient, and it removes the need for polar filtering, which is a real sin that we've been doing for a long time. But the problem with the non-latitude longitude grids is they're typically hard to analyze on the native grid. You have to do some sort of interpolation, typically onto a latitude longitude grid. But then you have a problem with all your dot products, i.e. your transports, the things, the heat transport, the water transport, the things you're interested in a lot of times. They have to be pre-computed on the original grid, and that leads to more storage, because kind of like Noah's Ark, you end up with 2 of everything. And then there's also other various analysis issues that come along with that. But the grid issue is a real issue, and it's clearly coming. The atmospheres, a lot of the new atmospheric models have non-latitude longitude grids, and as I said, the oceans already don't. On the atmosphere side of things, there's all sorts of new convection and boundary layer schemes coming. The clouds are coming. I'm just going to mention all these things, and Norm, there's your vertical levels for the top of the model. It's coming. In my quick survey of the community, I kind of hit 3 different types of ways people are going. Right now, most people use mass flux, what are called mass flux schemes. And they assume that all the vertical motions in the box are actually balanced in the box. And so now there's schemes that are allowing that to happen external to a grid box, where you have your subgrid scale things or velocities are being balanced outside the grid box of interest. The Donner scheme is an example of that, where you have multiple subgrid scale velocities are actually being forecast in a conceptual way. It's almost like tiling the vertical velocities inside a grid box. There's the so-called super parameterizations, which is you run a very high resolution 2D model inside of each atmospheric grid box, and then somehow average the various fluxes together to get an ensemble average for the grid box. And then there's also an idea that's floating around, I'm not sure if anybody's actually going to do this, is run multiple convection loops, each with a small perturbation, and then average them.
Why do you need to average them? Why can't you just pick up one?
That's a good question, and I don't, at this point I'm not justifying them, I'm just saying it's something that could come. For clouds and boundary layer, I kind of lump them together. Just to note that the tropical stratus clouds are either very important or the most important, depending on your definition of very and most, component to determining the climate sensitivity of a model. And there's a whole lot of schemes being tested. There's in the US, I know there's a climate process team that's working on the boundary layer aspects of it. As an aside, I note that the impact on climate sensitivity of a given scheme is model dependent. I used the inclusion of the Locke et al. Boundary layer scheme in the GFDL model and the Hadley Center model as an example of that, whereas when we put it into our model, the climate sensitivity went from something around 4 to something just over 2 degrees for a doubling of CO2. And when the Hadley Center put it into AOGCM3, it didn't impact their climate sensitivity at all. And just to note that these things aren't linear and depend on lots of other things. For radiation, the thing that I've heard talked about is that there's a standardization of a code, and that folks are going to try to use a common code a lot of different places. I think it was actually coming from the ECMWF, but I'm not sure of that. But if that actually occurs, that would be good, because that code would be, radiation is a subgrid scale process where you actually do know the right answer. And so you can test it with the so-called line-by-line models. And if we use a common code, then there's hopefully less chance of code errors, because you have more tests of a given code.
I'll give you an anecdote with respect to that. Bob Sess, you may remember, ran this atmospheric radiation intercomparison experiment. And for a specific scenario, models came in with their results, and they were pretty widespread, but there were outliers. So then he gave them 2 more years to work on their code, and then they would rerun it again. They reran it again, still the same widespread. So we asked, how come these guys who were the outliers didn't sort of actually move to the center? The reason was because the outliers thought they were right and everybody else was wrong. So whether this really happens or not depends upon human nature, I guess.
Outliers are not always there because of technical.
Were they right or were they wrong?
Some of them were right and some of them wrong, I believe, is the answer to that question. It's what you would expect. You probably could still get an argument on who was right now. For the dynamical core in the atmosphere, historically, folks have used so-called grid point finite differencing and spectral finite differencing. The finite element or finite volume of S.J. Lin is something that a number of folks are using, and he's just developing that on a cubic, what's called a cubic sphere, which then is a non-latitude-longitude grid. And I did bring up the simulation of southern hemisphere jet in that regard. And in the AR4, something I looked at is the simulation of southern hemisphere jet, because it's very important for the ocean, where that wind stress maximum is in the Southern Ocean. And the Southern Ocean is important for climate change because it's a region where a large fraction of the future heat and or carbon and or virtually any other tracer you can envision in the atmosphere is being exchanged with the ocean. And this is a latitude by amount of stress at each latitude for various models in AR4. And if you just look at, say, the two blue lines, there's one here and over here. The blue line with triangles is one version of our model with a finite difference dynamical core, and the blue line with the circles on is this SJ's finite volume core. And the black line is the observations. And the first thing I should note is that virtually none of the models do a particularly good job of simulating the observations. I was really surprised that all these models I hear with the maximum wind stress is as much as 10 degrees off of where it's supposed to be. And I have been outspoken in saying that if this had been in the northern hemisphere, people would have fixed it a long time ago. But yeah, it turns out one of these bad models is the Australian model, so I was really surprised at that.
That's bloody shocking.
Yeah, it is. But this really messes up the ocean in the simulation, and it, as I said, impacts the response of the model to future increases or past increases of greenhouse gases. Now, the vertical levels, the AR5 models are almost assuredly have more vertical levels in the atmosphere and a higher top of the model. The top will probably be up near the top of the stratosphere instead of kind of in the lower stratosphere as they are in the AR4 models. And that allows for the improved stratospheric simulation and interactions with chemistry in the troposphere. But of course, it slows the model down a little bit.
Okay, one thing it does impact just having it at the top of the stratosphere is to the extent anyone wants to look at solar forcing and the ozone response, it's not really high enough. Because
Yeah,
solar
exactly
forcing
where you
is
put
down
it
low.
is there's a
60
problem.
is much better. But of course you would like
Well, it depends. There's problems almost every place you put it.
No, I'm saying 60 because 60 is in photochemical equilibrium.
Right. On the ocean side of things, there'll be more folks running these non-latitude-longitude grids where the pole is either in North America and or in Eurasia in the northern hemisphere. There's probably be a lot of work on what's been called a generalized vertical coordinate, where there's something like a depth vertical coordinate in the model top to model the mix layer, something like a sigma level for the bottom, and in the middle the isopycnal levels. There'll probably be more folks who'll be using the something came in AR4, and more folks using as a free surface and true water fluxes. Historically, people have used a rigid lid in the ocean to filter the sound waves, so you didn't have to have a real short time step. And along with the rigid lid, instead of when water would go into the ocean, instead of inputting water, you actually remove salt. And it's what's called a virtual salt flux, and there was uncertainty associated with that parameterization. There'll be more tides and bottom mixing. the tides will probably be implicitly included through increased mixing in various mixing schemes like KPP. They won't be explicitly modeled in the models. There'll be some sort of estuary or river mouth mixing. And then the various tracer evection schemes are getting better as prompted by the needs of the Earth system models. The carbon in particular, moving it around has been forcing the various evection schemes in the ocean to get better and better. And then again, there's CPT efforts on the overflows and the eddy interactions with the mixed layer and so on, various physical parameterizations. In the sea ice world, the various elastic, how plastic the ice is matters, and then various parameterizations for ridging. More thicknesses. These are, you got multiple thickness categories inside of one grid box. The snow and the ice parameterizations are becoming more complex, and as well as having multiple layers inside of the ice. And then things like brine pockets and various other things that happen internal to the ice. And just note that as the ocean's models become more non-latitude-longitude, the ice typically sits on the same grid as the ocean model. Yes?
Can I ask a non-modeler question? I mean, in the past, it seemed like sea ice was a big issue that was very challenging to get it even close to right for the present day. So how, just over the last 5 years, I mean, how much has that improved?
It's still a challenge. It varies a lot from model to model, and on the quality of the simulation. There's still, I think, on average, remarkably, there's very few people that get both the edge of the sea ice right and the thickness in the Arctic right, or the Antarctic right. I don't know if there's any model that gets them well simulated.
Quick question. There is increasing probably the position of aerosols and stuff on the ice, which tends to change the albedo.
Right.
And that might have some climate impact. Is that something that the climate community is considering?
I know isn't it in your GIST model already? So it's in some models. And I know
It's going
folks,
into our model, into the end.
yeah, and
It will be.
and I think it's going to go into ours also. So the answer is yes. It's being, now whether it's how sophisticated it is, yet another issue. Yes.
Another response to that question is that for the southern hemisphere sea ice, it's a really tricky issue because there's so much vertical mixing that occurs in response to sea ice growth. And it's really hard to get that right, to get the seasonal variations exactly right. And it's issues of vertical resolution and how you really mix in the vertical.
Right.
But if the wind jet is in the wrong place,
Yeah,
as well,
it's
it's not
sunk
necessarily the
before.
fault of the ice model.
Well, and the other problem in the southern hemisphere, that's in terms of for sea ice, it's almost as bad as having the wind stress being mislocated. Is typically the clouds in the summer aren't bright enough, whether it's because there's too few of them or they're just not bright enough, and so there's too much radiation hitting the surface of the ocean, which makes it too warm, which is yet another problem.
Ron, I have a question. What about when you have the land portion being done in a gridded framework and the ocean portion being done in a spectral framework or non-gridded? It seems complicated to the boundary between these.
Well, the coupling is yet another. That's something I actually didn't hit. That it could have. Is the coupling between the components is becoming both more sophisticated and more standardized, and how it's done. And the couplers themselves are typically conservative, and so the properties are being conservative. But the interpolation between one grid and another is a non-trivial issue, because you can end up filtering your variance as you're passing fluxes and all sorts of other issues. On the land side, dynamic vegetation, I think, I keep stepping on your foot, is coming, which introduces new time scales into the system, not necessarily longer, it's just that like for forests, they're typically centennial time scales. The idea of fire and more land types and then land use are all things that are either coming or arrived. in some models in AR4. The idea of tiling, which is having multiple subgrid scale heterogeneity. River routing schemes are becoming more complex, and then land storage and the buffering of river flows. Having multi-layer snowpacks is, I think, something is coming, and then paying attention to the soil-water phase change, and then having multiple layers of that.
Does the fire component consider things like suppression or no suppression, or is it just wildfires? Or?
Typically, it's non-human caused fires. So that would be the way I would describe
Although
it.
there are models in other parts of the community that go into that in great detail on both
Right.
those issues. So.
Right. But I think the kind of the IPCC class communities are just starting to get their toes a little bit wet in this regard, because it's something that has to come.
Hot, not wet.
Well, or wet or burned, yeah. But it's something that has to come along in a sense with the dynamic vegetation, because it is an important part of getting the natural vegetation right.
Another thing that people are using, for example, at Goddard, are having sort of river valleys, so that the grid for the land surface hydrology is different from the atmospheric grid.
Yes.
And then you have the translation issues.
Yeah, I didn't have that on. That's river routing. That's what I meant by that. It's connecting all your grid boxes in the land to an ocean grid map.
But you might also choose to have an irregular land grid.
Right, that's the point.
Yeah, yeah, you
would
can
make
do that
sense,
too,
yeah.
right.
Chris, as we are thinking beyond 100 years for long runs, the change in the type of vegetation might become an important aspect compared to just having in dynamic vegetation model, the species growing or decaying or disappearing, but changing vegetation. Will the land model be able to do that by then, by 2000?
Some of them, some groups. I know the model we're working on is trying to do that. In fact, I've run an experiment already where I managed to kill all the trees, which is the ultimate in changing vegetation.
And you couldn't print out the results.
So there's
a PDF.
There's two kinds of, you can think of this in two ways, right? So you can think of vegetation being dynamic in the sense that you don't change the vegetation type, it just grows and dies in place.
Right.
Or you can have vegetation
Be
actually
predictive.
move around.
Be predictive. Yeah.
How the trees can be
Yeah.
planted.
Yeah. The one we're playing with is predictive.
So the vegetation can move around.
Yeah. There's good news and bad news with that.
But then you get if the rain is falling in the wrong places, you start
You're sunk.
growing.
That's
Yeah,
right. Yeah. The Amazon's not a rainforest in our model.
What is it?
What is the time frame in which you need to go to the second type of model? I mean,
Seems
if
to
if
me
you
it
run
goes
for
with
100
the.
years. Do you need to get into that?
Yeah, I think so, because it goes with the carbon cycle modeling. I think.
Especially in the Alps.
I don't know why you would. It seems like it's tightly coupled to the carbon cycle modeling, for one thing, to me.
The
Oh,
CCSM,
these pictures aren't coming out at all.
The
let's
CCSM
look
could
at
probably, in principle, do both of those things that Jerry just mentioned. I would
That's a
also
lot
say that
better.
the Arctic is the place, and actually what CCSM doesn't have, which is probably the most important thing, is actually having shrubs included into your hierarchy, which is going to change
I'm not gonna
very
make it
quickly in the next 100 years,
much
whereas trees won't change nearly as quickly. That's something that we aren't able to do.
Yeah, but then that becomes a coupling issue, because if you have errors in the precipitation and it's trying to grow the wrong plants in the wrong place, you have to do something about that, or else the whole
Or
thing.
live with it.
Yeah,
Sure, it means your physical GCM has to
I
be
mean,
equal to
that brings
that.
up a validation question, doesn't it? I mean, you have to also establish criteria for acceptable performance.
Yeah.
Is that part of it?
Absolutely. In fact, that's 3 slides from this one. That's a real issue, is what are the metrics for declaring success in this game? And so I threw these slides in because it's something that we've talked a lot about inside GFDL, and I know at least the other groups that have been working with have talks inside, but I'm not sure there's been any crosstalk among the groups. I think there's 2 basic ways to build your ESM. One is to start from a working physical climate model and add the additional components, and the other way is to try to develop both in tandem at the same time using one code, one model. what I see is the pros and cons of both. So when you're starting from a working physical climate model, the pros is you have a known solution. So then it's easier to identify the problems as you're adding in new components, what they're due to, both in terms of simulation and just code bugs. And to my knowledge, all the successful ones, at least in the kind of the AOGCM community, have so far been using this idea of starting from working physical climate model. The cons of this kind of idea is that simulation of key places might be lousy. And again, in our coupled model, we're in the process of doing this now. The Amazon is too dry compared to observations. And so in our model with dynamic vegetation, the vegetation is coming out is partly savanna, grassland type, and partly rainforest type instead of being all completely easily rainforest. And that's a problem. Another problem that you can run into is that the code may not be structured for coupling in the new components that you're adding, which can lead to a lot of coding headaches and somewhat offset this pro on the top. The second basic way is develop them in tandem. The pro is that the code all works. When you get done, everything works together and there's no issue about having to throw in anything more to the code. And you have the ability to address the couple problems directly during your model development. But that's a two-edged sword because your debugging takes longer because the ESM runs slower. And that makes it harder to debug just because things take longer. And then it's also harder to debug because everything's coupled. And it's harder to identify where your problems are coming from. And I didn't know of any examples of success, and probably you folks in the room would be better than me, but I don't know that anybody's actually been successful at this.
Well, on model of intermediate complexity, yes, but not on big model. Because
Okay.
they tune so much.
Right.
I mean, that's another approach.
That's another approach, is EMIX. In EMIC, it would be easier because you can take a lot of the icky things and make them simple.
It still makes sense, though, to look at each component separately with the observations first, doesn't it? I mean, that's
Absolutely.
How you do it. You get
Yep.
some models that work, you put them together and they don't work, and then you tweak it.
You have to couple them at some point. It's
Yeah.
just a question whether you do it, how you do it, and when you do it.
I mean, if we
But
get to
isn't the
situation-
advantage, isn't there an advantage to doing both ways at the same time, in parallel? To work with isolated components and then very rapidly test those isolated components in a coupled framework also.
I guess, to me, is I would develop a physical climate, the way I would propose, and this is the way I've argued inside of GFDL, is to build a physical climate model first with the code that you can couple in all the Earth system components that you want to add. You develop metrics that reflect not only the physical climate model success, but the Earth system model success. For example, you will pay attention to the Amazon rainforest, like we didn't do when we were developing the physical climate model last time. So that if you can identify what those key places are for your Earth system model, then it's, I think, possible to go that route. But I don't know what it means to really do them all in parallel, because these efforts are huge, and to build our last couple model, physical climate model, consumed virtually everybody inside of GFDL.
Well, what I mean is that
There were nobody
within every
left
6
over.
months or so, you actually attempt to run a coupled model with
Absolutely.
a dynamic vegetation model simultaneously.
We do, yeah, I would agree to that. That assures that the code flows.
Not just that the code flows,
that
but you
doesn't
can
look at
watch
simulation.
whether you can immediately see trends, even though you're not at an equilibrium. You can see trends in the various components of the system, which are providing hints about problems, I think.
We will disagree, but yes.
Ron, you talk about this expanded set of metrics for gauging success or whatever. That raises, to me, I
That's my
think, a
next slide.
complex set of questions. Is how do you weight these different metrics? I mean,
Right,
is a model
absolutely.
better that gets the Amazon right, but the rest of the world
That's
wrong?
absolutely, that's correct. Absolutely. You get into those arguments real fast. The other problem with any list of metrics is, to work well, they have to be short. For for example, when we developed our physical climate model last time, we only had 3 things that we said if they weren't right, we were going to stop the process and not claim success for a physical climate model. One was the thermal handline circulation in the Atlantic. One was that the SST annual mean errors at any location over the ocean were no larger than 6 degrees C. And one was that the El Nino was decent as defined by the El Nino folks that were helping build the model. So we had 3 things that we were looking at. We only had 3 things that would stop the process. Everything else we thought we could live with.
Were those roughly equally weighted in your?
Yes, they were equally weighted. Any of the 3 would have stopped the process. So I think that again, inside of GFDL, I argue that we can add 2 more, make 5, for our next model. One was going to be the Amazon rainforest, and people are arguing like cats and dogs over what the 5th one's going to be.
Are you going to leave the other 3 the way they were?
Yeah.
And is there more than one number associated? Like for ENSO, were you looking at time scale and amplitude?
Yes. Yeah.
Because you did great on one and not so good on the other, right?
We can talk about that.
I mean, we did worse, much worse. Don't get me
Well, I
wrong.
don't know
But it was
what
just like
great. The frequency is almost right on, and the magnitude's too large. But there's a lot of variability in time. I could show you another 100-year period where it looks great. Okay. So.
What are some candidates for the 5th, like sea ice? Or?
No, they're all for Earth system model metrics of various ilks. Whether the carbon is stable in a mixed layer run, an atmospheric mixed layer run, various other kinds of things like that. What's the vegetation look like?
Can you explain that why you would focus on the Amazon rather than some more aggregate?
Pardon?
It seems surprising to me that you would focus on the Amazon as in the top 5 as opposed to some diagnostic about the global carbon cycle, like the air-sea exchange of CO2.
The Amazon was viewed as a place where a large fraction of the carbon is sitting and might change in the future.
Possibility. Yeah. But you could also, presumably, also have metrics a bit like RMSO and surface temperature, a metric that's equivalent for vegetation cover.
Yeah.
So, you want it
Net
to look a bit
primary
like a real
production
world.
or something.
But you could argue boreal soils or have an even larger storage of carbon,
Right.
or,
Yeah.
So there's a debate that happens to
Absolutely.
build this list.
Yes. And so,
You can change the metrics.
yes.
I mean, this is one reason why it's so good to have different models, because different modelers will have completely different metrics.
That's
For
right.
example, a GISS, what Jim Hansen was interested in was the net radiation balance at the surface and at the top of the atmosphere. Did it match satellite and ground-based observations? He figures climate change is a radiation balance issue. That means clouds, that means radiation. So that was the overwhelming thing. Anything else could be sacrificed for that, in fact was, to some extent. But that's why it's good to have different
We had
people.
we had things like that in ours also, but they weren't showstoppers because those are relatively easy to tune. I mean, you can play with your clouds.
Does that mean there was another class of metrics that you watched over but didn't view as critical? Is
Absolutely.
That, okay. So the 5 are really what you call showstoppers.
You're- That's actually the inverse of showstoppers.
But that was assuming the tuning was done on these other guys. That was assuming the tuning was done on
Yes.
these other guys.
Yeah, we can get into all the details of how you built, at least how we would go about constructing a physical climate model, but that's another hour talk. Yes.
Okay, one thing that always, you guys tune to basically your present day climate,
Yes.
which is in the middle of actually a secular climate change.
Yep.
So
These areas are so gross, you don't have to worry about it.
yeah, I know, but as the models get better and you start looking at things like precipitation on regional scales, you're going to have to do time-dependent verification to get to the 20th century.
Yep. Yeah, and that will be done, but that's harder to do because that requires a whole initialization process. It takes a long time. So those kind of things get done, but typically they're not done very much and are done right at the end of the process. So I think we've hit all those things. Just going to hit couple model initialization for the physical climate system has been something I think that's been made a lot of progress since the TAR. There's a lot of standardization now. And most physical climate models for the AR4 use some variant of what we wrote about, where you develop a couple model, you become happy with it, whatever metrics you choose, and then you start from a present day initialization, you set your radiative forcing back to some period back in time, and you run the model for several centuries to a quasi-equilibrium state, and at some point in this run you declare the start of your pre-industrial control, and off you go. It's the typical method that's being used in the AR4 models. There were a number of standardized runs that were used. There was this long pre-industrial control. There was also a present-day control that was usually what was being run to actually evaluate the model when it was being developed. There were a number of idealized forcings. There was a 1% per year CO2 to doubling of 4 times. There was the so-called stabilization run about present day, and by stabilization, all that was meant was that all the radiatively active constituents were just held at present day conditions for a period of 100 years, and you let the climate come into adjustment with that radiative forcing. There was a similar thing done with the A1B and B1 scenarios at 2100. There was what was called a historical forcing from the pre-industrial up to present day, and a future from present day out to 2100. And there was also a control and 2 times CO2 atmospheric slab ocean integrations to determine the climate sensitivity.
There was supposed to be an AMIP run too.
Yeah, you're right. I forgot about the AMIP run.
Ron, do any of those include land surface changes during the spin-up?
During the historical, some models did include land surface. What models used as their forcings for the historical vary from group to group. Some did, some didn't. So this is a schematic in time and in CO2 amount of all these various runs. So these 2 guys here, the 1% per year is to doubling, and the 4 times. This is the long control. The black line is the historical run. This is the present day stabilization. This is B1, A1B, and A2, and these 2 of them also had stabilizations. So as you can see, all these runs add up to several centuries of integrations, most groups more than 1,000 years worth of model integrations. We're done. So what we learned when we were doing these runs is that these idealized forcings where you do 1% per year, that allows a comparison of the model response to a common forcing. It's almost a stereotypical MIP kind of thing, or model intercomparison. The radiative forcings from model to model for 1% per year do vary, but they only vary a little bit in relative to the big differences in the response to that forcing. The stabilization allows the investigation of the physical climate to so-called warming commitments, or whatever word you want to describe. It's just looking at how the climate system evolves after the radiative forcing is held fixed, and looking at those time scales. Of course, the historical runs allows the model evaluation of the model response to the historical climate changes. You can see how well or poorly the model's done. You can actually also do attribution of changes. And then, of course, the future is this the projections of future climate changes. And then, as I said, the mixed layer runs allows the computation of climate sensitivity. And this is a summary slide of that stuff I just kind of went through very fast. That there's this standardization, these types of integrations we perform. There's something that's very good with everybody doing the same kind of runs. It allows for both realistic and idealized model comparisons to both observations and from model to model. And we need to find a similar set of those integrations for the Earth system models that we'll be developing, and that the number of integrations is an issue, and it's the use of the CPU time. and the data volume and what's archived is another issue. Both of those are big issues in the community. And for data issues, this is kind of the last slide. These models generate tremendous amount of data. And the problem is one of the resolution, but it's also one of timescales. There's people looking at our models from everything from diurnal variation out to how changes happen on centennial timescales and longer. So the archiving of data is a real problem. There's both for resolution and timescale. And of course, when you add new components and you have more predictive variables, you can easily double or triple the amount of data you're archiving. The non-latitude-longitude grids is something I hit right off the bat, and that's going to continue to be a real problem as we're collecting data. There's always the problem of what the variables to archive, what timescales are archived, and then what data we actually give out to both each other and to the community. And how do we do that? Do we all send our data to PCMDI like we did the last time? And they have, what is it, 20 or 30 terabytes of data?
Actually, we have more than we have but yes.
Some
40.
Okay.
Count all the jury stuff.
There's a whole bunch of data sitting at PCMDI. My guess is for the next go around, that'll easily double or triple. You know, can we send it all one place, or we're going to do distributed data serving? And how's that going to happen? What's the coordination that's going to happen? And then the CF convention. And for those of you who don't know what the CF convention is, when you write data out, typically it's written out in something called NetCDF, and the CDF of NetCDF stands for Common Data Format. And there's both your data, and then there's information that sits on top of your data that describes what that data sets are. And what the CF convention does is define what things belong in that so-called header amount of data. And virtually everybody that knows about it wants it, but there's really yet nobody that really has oversight of the whole process. And I describe it as a mom and pop organization so far.
There's actually been a lot of progress on that in the last
There's-
few weeks.
Okay, but it's also progress coming, but it's still not,
Ron,
we're
has
still
it
a
been
long
in-
way from there.
I've been aware of it for a long time, but have there been problems with the evolution of the CF convention up to now that you could see?
The problem is we're burning out Jonathan Gregory, who is the main driver of the convention, and he spends a lot of his time just answering people's questions from actually. The convention is now broader than just the modeling community. It's serving all sorts of different communities. And so there are fights about what standard names are for variables from various other communities that he actually has to monitor. It's things like that.
Have you talked to him lately?
Not lately.
Okay, there's been, it's better than you're
That's good.
portraying there.
Yes.
So with respect to that, and Linda can comment on this too, I've heard from a number of Working Group 2 people who want to use the model data for impact studies, that they basically find the whole process very non-user friendly. And in fact, somebody made a comparison to when Roy Jenny was doing it at NCAR, where he would work with the people to try to find out what they needed and how they could best get it. And that whole process worked from their perspective a lot more than this sort of automatic approach, one thing suits all, which doesn't end up suiting a lot of people. And you might say they should get better at what they're doing, but in any event, that's just the impression I've heard.
Okay.
Yeah, I'm just I've heard the same thing, and a lot of the impacts modelers, both in developed and developing countries, just don't have. We're coming from a standpoint, a place like NCAR, we have these huge computing resources and a lot of trained staff, and it's not like that on the other end. So,
Serving of data to a wide range of users is a non-trivial exercise. It in some sense, almost can't be handled by software because the users themselves don't know the right questions to ask or what the issues are.
Yeah, but I mean, this is a necessary part of science. If you know Roy Jenny as I do, you also can remember the days where you would go into his office, or one of the people who worked for him,
and ask him for a bit of data, and they would kind of hold their chin for a few minutes and walk over to a stack 6 feet high and pull out a pile of paper and or a deck of cards and hand it to you. You know, I mean, we have to have an automated process for this, and maybe it can be made better. But we need these automated metadata and conventions.
Yeah, I think that's
Can I
what people are
defend the
hoping
system
for.
a little bit now, so I can explain it? First of all, the people who've used it on the working group 1 side have been very, very happy with the system as opposed to what happened before. The other one was working, when this first came up in Hamburg, what, 3 years ago now?
Yeah.
We made a decision, a conscious decision, and it was one that we at PCMDI drove from just the ability to handle this and make it a tractable problem, was the audience for this data set was the working group, potential working group 1 contributors. By definition, because we are that. I mean, we have scientists like Ben Sander, Peter Glucker, people work in our group that understand that. We knew we could tackle that problem and hopefully be successful with it when we declared it at the time. We did not understand enough about the other work groups, nor did we have the resource. We did this with no extra funding. In fact, I have fewer people now than I did 3 years ago, and we still took all of this on. So, you know, it would be a very personnel-intensive operation to do what you described. Now, that's not saying it shouldn't be done. I'm just saying we tried to do what we said we were going to do, and I think given the success of the Working Group 1 report, we accomplished
It's still
that.
an issue for the future, and you're not going to be able to solve it without that additional funding.
Right, and this is an issue perhaps
So it's
to
for
be
the
brought up in
community. It's
September.
something, yeah.
Right, but I'm just saying, I'm a little sensitive to criticism that what we did isn't serving the audience, because it is serving the audience we declared it to be, and your complaint, this is why I keep punting, every time this question comes up, I keep punting it back to Jerry, because we work to make sure this is done under WGCM auspices, and they're the policy setting body, not PCMDI.
You could probably add something.
Probably can. Dave is quite right that it was set up only for Working Group 1 purposes. And so if anybody is to be criticized, it's not Dave per se or PCMDI, it's the co-chairs of the working groups as to why there wasn't better coordination between the 1 and 2 and resources established for that. And one way in which the slack was taken up was to move some of these data sets in a, let's say, to make the format more friendly to the data distribution center. And that has been done, in point of fact. So there are venues for the Working Group 2 community. However, I certainly think we should do a better job on having more than one working group served the next time around.
So it's an
And
issue
maybe
for
Rich,
the
let
future.
me just add, I want to
It's
compliment
beyond
Dave.
you.
I just want to compliment Dave and his staff for working so effectively with the folks in the IPCC DDC and getting the data over to them. That said, I don't disagree that the resources that we have available through the IPCC DDC are at all adequate. And right now we're undergoing a change ourselves in the UK portion of the DDC, which has been based at Crewe and was originally set up by Mike Hume. David Viner has been running that, and I think there's been a slacking of interest at Crewe in this whole thing. So now the UK government office that's responsible for it is in fact putting out a new request for bids for a new organization to run that portion of the DDC. So that's, you know, adding some stickiness to the process, but we do need to get more resources on this.
I was at the meeting where Dave said it was only good to serve Working Group 1. Even at that time, we weren't, I would have thought 100 users would have been an outrageously large amount of users for this data, and I think we're at like 600 or...
Yeah, we're still getting requests.
We're still getting requests, so he actually, for what he volunteered for, he did remarkably well.
Tell us how much data you said I was going to get too, Ron. Remember that?
Yeah, it was 10 terabytes.
Yeah.
Yeah, just a quick comment. It's not that automation isn't useful. It's actually critical. It's just that different automation is needed for different users, and that, you know, some of that's been done, and it
Yeah,
probably needs to
could
be
you clarify, is it now, do you understand what your needs are and you can define them at this point?
Well, actually, I'd hunt that to Richard or Linda, but for example, one example would be if I'm running a climate model, you know, I need a global grid, I might need 2 or 3D. doing impact model, I need the difference. I need a time slice of one grid, you know, over a period, and you know, and that's a completely different automation to give me that. And if you give me the whole 3D time slice, I probably can't handle it.
Well, the thing is, now if you look, if you go to the site, subset, this, we're continuing to improve, this is not, I'm sorry, I didn't mean to interrupt your talk, but just let people know what's going on. There are tools available, you're going to have some software development on your own, but we have the OpenDAP server running. You can do subsetting and aggregation from a client.
That's not a criticism at all.
I'm responding to say there are more tools out there now than there were 5 months ago. And the biggest complaint we had was the subsetting and aggregation, which we recognized as the beginning would be a problem.
Yeah.
But we had to make some compromise because they wanted all this done within 11 months too. That was the other factor that goes into this. And for people who want to go look at it, you can do subsetting and aggregation, but you need an OpenDAP client on your end to do that. We don't do it for you, but you can do it. And the information is there about how to install the software on your system to do it.
Well, I think that shouldn't be taken as a criticism or anything from BCMDI, but there is an issue for the next IPCC, is how to treat the data so that they can be useful for the 3 working groups. And I don't know exactly where that should be discussed. Probably the chair of the entire IPCC should take that, and he hasn't done that, obviously. But maybe we could make some recommendation about what could be done in the future to expand basically what BCMDI has been doing so that it can be automated for other groups and other working groups in particular. There are the issue, for example, of should the database be centralized or should it be decentralized to a certain extent? We don't know that. Depends on the capability of BCMDI in a few years. But if it had to be somewhat decentralized, then we need to find partners, and that takes some time. And so, at one point, this group could make asking recommendation on that and send it to IPCC so that they start thinking about it.
So this last slide is to return to something, at least inside GFDL, we feel feeling very much, and this is how to spend our additional resources. And that's my summary slide of the talk.
Okay, thanks, Ron.
Are we going to be applauding or not applauding?
You can applaud.
A delegated applauder.
Well, we could tape it just once and then replay it.
I guess we'll get any more questions.
There you go.
We'll form a subcommittee to address the applause issue.
Okay.
So I think we can take a break now and reconvene here in another